everyone. Bravo. Thank you so much for coming to my talk. I know there are lots of other great talks here, so I appreciate it. Nice to see you. And before I start, I just want to call out that this auditorium is so colorful and amazing. I really appreciate that. I'm a little colorblind, but I still see the colors, and it's beautiful. My name is Kevin Maes, and I'm a software engineer from the United States, currently living in Spain. And over those 20 years, I've done a nice combination of product development and project management, people management, consulting, all kinds of different things. And I've worked for small companies, startups, and also large companies, largely in New York City. For the past 2 years, I've been super fortunate to work with an amazing team at Stately, where we build visual diagramming tools for engineers and teams just like yours. And it's based on an open source state machine library called XState. So I mentioned Spain, and this is where I now live in Malaga. And every day I wake up to the sights and sounds of birds swarming around in a mesmerizing way. It's really quite beautiful, except for the sound and the construction. And I recently became curious, this made me kind of curious, about algorithms that are inspired by nature. And that's when I stumbled upon genetic algorithms. Now, these are known as GAs, and they're nothing new. In fact, they're actually part of a broader category called evolutionary computation, which itself is a sort of branch of artificial intelligence. And their origins go back many decades. So let's go back to the 1960s. There was a computer scientist named John Holland, and he was also a professor at the University of Michigan. And he was inspired by Charles Darwin's theory of evolution by natural selection. Now, his work basically tested to see whether biological evolution could somehow be applied to artificial systems or computer programs in order to make them more adaptive and intelligent. In 1975, he wrote his groundbreaking work, which detailed the theory and practice of GAs. This combined biology, computer science, math, and all to solve optimization problems. Holland is known as the father of genetic algorithms. Let's talk about what these are a little bit. The main purpose of a GA is to basically arrive at a desired behavior or an optimal design or to solve some sort of complex search problem. So we want to do that, though, as quickly as possible with a GA. Imagine you're given some sort of problem to solve, and you have an infinite number of attempts to do it. Eventually, you'll possibly land on a solution, but it'll take a very, very long time. So GAs use the concept of natural selection and survival of the fittest as a way to sort of speed up that process to arrive at your solution. Now, what kind of problems can be solved here? Well, they can definitely be used to design efficient network topologies. So I'll give you an example. A company like UPS for shipping, they've used GAs to optimize delivery routes, okay, to maximize efficiency and to reduce cost. Also, there are evolving game strategies in games like Go and chess, and they can use GAs to enhance their AI. Educational institutions can also sometimes solve complex scheduling problems to ensure conflict-free timetables. And GAs have even been used in the production of hardware. So, for example, NASA successfully deployed what's known as an evolved antenna, where it used a GA to design a tiny little communication satellite about this size, and it actually deployed it into space. So how does a genetic algorithm work? Well, there are several steps in a GA. The first one is population initialization, and this happens only one time at the start. The next is evaluation and fitness. Then we have selection, crossover, mutation. And those last four, they happen repeatedly in a loop, maybe hundreds or thousands of times. And each of those iterations is considered to be a generation, each with its own new population. Now, these GAs are going to manage a sizable population of what's known as individuals, or members, and these individuals will each contain potential solutions to the problem. And those solutions are stored or encoded in the individual's DNA. Now, DNA here is a kind of representation of the individual's characteristics as a solution. And it's important to note that population initialization is where we can first establish a wide variation for the population. during evaluation, we let the individuals do their thing. Basically, they attempt to solve the problem. And this could be interacting with their environment or doing whatever they're trying to do to solve the problem. But the most important part of this stage is the fitness evaluation. And using a fitness function, we're able to evaluate performance. We can give them a score, we can reward behavior, we can punish behavior, and every one of the individuals will be assigned a fitness score. Now, during selection, only some of the individuals will be selected to be parents for the next generation. And this gets interesting because there are different techniques for selecting those parents based on fitness. One of the most common is roulette wheel selection. So in this method, the likelihood of being selected is directly proportional to the individual's fitness score. If we added up all the fitness scores, we would get a whole pie. And then the higher fitness individuals would obviously take up a disproportionate amount of that pie. But then when we randomly select a number, or an angle, we will land somewhere on that pie, giving a greater chance of landing to someone with higher fitness. However, it's still random, so it is possible that a lower performer could get chosen, which is still good for variety. Here in crossover, that involves mating parents, and we need to maintain the same population size from generation to generation. So for each child, we're going to select some chromosomes from either of its two parents. Mutation is interesting. We have a chance to maintain variation during a mutation step. And we need variation in order to avoid achieving something known as local optima. And that's basically when a population seems to converge around what it thinks is the best solution for the immediate area, but in fact it's not the global optimum, which is the best overall solution. Mutation can be calculated according to some sort of mutation rate and a mutation amount. Okay, so now that we've created the next generation, we're going to return to the evaluation step, and we're going to see how the new population handles the problem. Now, we can think of GAs as a sort of problem-agnostic approach to solutioning. And now that we know a little bit about GAs, let's take a break to something else for a bit. Now, back to my new home in Malaga, which I love. Sun, sand, culture, food, just as advertised. But there's something else that's really great in Malaga. Check this out. Okay, that museum is so much fun to visit, and there's a ton of nostalgia there. I don't know, maybe some of you even noticed the Atari 2600, which is that game console on the left there. So that was actually the very first game console that I ever played on. It was a long time ago. In fact, I never actually had one at home. I would have to go to the neighbors, and my neighbor's, the friend there, he would have one, and we'd play there. And one of the earliest games I remember playing was Kaboom. Here's a short clip of how Kaboom looked. Okay, so inspired by Kaboom, I decided I wanted to make a game. And I also wanted to see if I could experiment with adding a genetic algorithm to that game. But instead of one bomber, I would need a population of bombers, right? And I needed that adversary to be able to evolve to threatening levels like a Terminator evolved. Or maybe it should be something fearsome up in the skies, like a direct descendant of the great dinosaurs. So after a while, I gave it some thought, and I knew I'd found my match. Here she is. But doesn't she look scary enough? Well, I should warn you guys to never judge a book by its cover. My game is called Egg Drop. You know, like the Chinese soup. Do you know about the Chinese soup, Egg Drop? Does that exist here in North Macedonia? Anyway, give me the honor to introduce you to Egg Drop soup. It's a delicious soup. You drop an egg in it, you stir it around, it breaks apart. It doesn't matter. But the concept of the game is simple. There's going to be a chef who's cooking a soup. There's going to be hens or chickens up above laying eggs, and the chef is going to try to catch them. And the hens hope that he doesn't. Okay, simple enough. So let's get cooking. Now, I built this game using React, which is what I normally use for non-game applications. And for creative coding projects, I usually turn to Canvas or sometimes P5.js. But in this case, I was curious to try something called Canva, since it's known for its smooth combination of React and Canvas together. Canva is free to use. And also, I know there are Angular folks and other libraries. There are Canva adapter libraries for Angular and Vue. Now, just want to note ahead of time, any of the code that I show, which may go very, very quickly, it's all available online. There'll be a link at the end to the GitHub for this project. So I found using Canva in React to be pretty intuitive and very easy to get started. Your overall app is represented by a stage component, and you can actually render several layers. There's layer components, and each one of those will instantiate a new canvas element on your page. Now, Canva uses the normal React props API to easily attach event listeners and to elements for interactivity, which one of its main benefits. Layers can help you organize better performance, depending on which ones are static or interactive. Now, another useful component is a group component, which helps you with relative positioning of elements within a group. Here you see we have components for things like image and rectangle, which are shapes. You'll see more features soon. So after getting a Hello World project set up, I thought about the various game mechanics. Who are my characters and how will they move? Who's interacting with whom on the screen? And how will the user interact with the game? So based on these, I set out to create a series of quick POCs or proofs of concept. So in this first video, you see a hen moving back and forth on the screen with linear motion. So far, so good. But now, she's joined by all of her girlfriends, moving back and forth, each within their own range of motion. We can effectively spawn a number of hens. Now, it's a little hard to see here, but whenever the hens stop moving, they get the urge to lay an egg. And not only did we spawn some hens, but now all of those hens can spawn a number of eggs. Now, for this type of linear motion, we can use a Canva tween. Now, if you're not familiar, the word tween basically comes from the phrase in between, which represents a series of frames that are between two keyframes. And together, they create the appearance of smooth motion. So we instantiate a Canva tween, we assign it a node. In this case, it's a React ref to a shape or an image. We can set the duration of the tween and its target position. So now we have a single hen, and she can lay an egg. And when the eggs land, they either transform into something else, or they just land flat on the ground. Okay. And at this point, the eggs now land, and they hatch into chicks, and they can run off the stage in either one direction or another. Okay. So we add here an abstract shape for our chef, right? And this player, the player of the game, can now move the chef from side to side by pressing left or right arrow keys. And the chef is going to have some speed limits and some light acceleration and deceleration. Our chef also gains a new power now, which is the ability to catch an egg. So he now has what it takes to win this game. And the chef actually needs to catch an egg in his pot. And the pot is smaller than him and moves relative to him, thanks to the Canva group. and he can try to catch as many eggs as possible. Now, catching eggs involves a form of hit detection between the chef's pot and multiple eggs. And in Canva and in Canvas, there are several different forms of hit detection, and they're all right here. But we're lucky in this game because we really only need to use a very limited form of the bounding box detection. So if the egg's bounding box intersects with the rectangle of the chef's pot rim, it's a hit. And for better performance, we can actually ignore detection in many other cases. For example, when the egg hasn't fallen low enough to the chef, or when the egg is not even on top of the chef, things like that. Okay, now the eggs here are a little bit more egg-shaped, and they also rotate as they fall for a more realistic falling experience. To get that egg shape, these eggs are now imported transparent PNGs. Let's talk about state machines. Okay, state machines, if you're not familiar, they are a way to model software such that your application exists in any number of states and can transition from one state to the next using events. Now, I've used state machines and the XState library I mentioned to model all sorts of flows in software development. Things like UI features, customer onboarding flows, fintech applications like trading orders, and also creative coding projects. But one of the best use cases of state machines, in my opinion, is in the development of games. The behavior and animation of game characters is so heavily based on states and events. And as a bonus, it's easy to produce a visual diagram from these machines and also to export these machines to code. So in this game, there are state machines for the overall application, the chef character and the keyboard input, the hen and her movement, the falling eggs that turn into chicks and run away, and also the game levels, the scorekeeping, the timers, audio, much more. Now, don't worry about every little detail. This is just a bird's eye view of the egg machine. And again, this uses the open source state machine library called XState. And yes, this is actual egg state code. Okay, I'm sorry, I'm a dad, so sorry for the bad yoke. Back to our prototypes. We now have separate Canva layers for static background, UI elements, and animated characters. We have a notion of a timer for each game level, and the state machine tells us when we're playing or when we're waiting for the next level. Here we just have a wider chef, makes it a little easier to catch eggs, and we'll give some thought to proportionality in this game as well. So now we've replaced the hen with an imported sprite image containing 2 frames, one black and one red. Now, at this moment she lays eggs, the hen state machine tells us to crop and reposition the image sprite to hide the black frame and to show the red frame instead. Okay, so we've seen a lot of prototypes. One sec. At this point, many core aspects of the game's movement and interactivity have been tested out. But the game looks like a bunch of moving shapes and a hen who's temporary stand-in. It's time to create some graphics for the game, so I reached for a trusted industry tool for vector illustrations. Not that one. This one. So DALL-E to be specific. And as you can imagine, things got pretty unpredictable, right? So the first order of business was to create the chef. He's energetic, persistent, loves to cook. I call him Chef Raffi after my son. I uploaded a real photo of Raffi to ChatGPT, and he turned him into a chef, and according to my prompt. So this is what I got back, right? We have a chef, we have hens, we have pots with closed lids, not very helpful. We have a severed head with missing nose and mouth. This is not what I'm looking for, right? Next, I got this one, which is actually pretty great, but he's a bit old for the part, so I might use it in the future. My third try, though, I got this cute chef. He's got an open pot with steam, good for catching eggs, spoon, some tears, random stuff. I think this is good enough. So I cropped the sprite here, and I imported 2 images of Chef Raffi into the game. Alignment isn't quite perfect. But he has a rectangle where the pot rim is positioned to catch the eggs. And I wanted to also try to have the hens lay eggs while moving, so that the eggs drift sideways based on the hen's speed, which would be a little harder to catch. Okay, so for this, we can no longer use a Canva tween. We need to move on to a Canva animation, which gives you greater control for every frame of the running animation. And we can calculate positions that go beyond setting a target and duration for the tween. Okay, in order to move around, this chef has to pick up his feet a bit, but he knows it's worth it because now we're keeping track of how many eggs he's caught in each round. Okay, we've gone from pink to blue for no reason, or blue to pink for no reason. But Chef Raffi, not the character, but my actual son, requested that we actually add colored eggs to make them worth different points. And so I said, yes, chef. Okay, next I went scouting for the perfect hen, and I had to put out a lot of prompts. I requested sprite images of a hen from different angles and positions, but accuracy was a big problem, and so was consistency. It's hard to iterate on images using follow-up contextual prompts. You know, you get an image you like, you want to make a slight tweak to it, you get a new image, and it loses all the things you liked, and it gives you the new stuff. ChatGPT's context window, just sees your prompts, but can't really evaluate its own image that it gave you last, apparently. So this is really like a whack-a-mole, another game. Okay, so you have to keep trying until you eventually get what you want. And I did, and I got this. And these look kind of nice, because they have different poses, and they even come with a matching chick. So I cast this hen for the role. Okay, now that we have raw images, we need to be able to manipulate them so that we can really turn them into characters. And I used a software called Logoist by a German company called Cinium. Now, this is for Mac, so I'm sorry if you don't use Mac, but they do really high-quality apps, and they go beyond logo creation as well. You can import raster images, and you can turn them into vector graphics. You can also arrange them into layers and edit them. I was able to focus on things like size and alignment to create various states. And then that way, when the hen is either walking or jumping or turned around, then the egg will always originate from the same X and Y position. So then I exported this to PNG. Okay, the next step is to create sprites. I used a software called Texture Packer, which is specific for this need. And it's very easy to use. You drop in your PNGs, you preview your animations, and sprites can be exported as a combination of PNG and JSON file with metadata for cropping and positioning each individual image. So here's our chick, for example. Okay. All right, so now you have all the character sprites. You could also put them all together in a big sprite if you wanted to. Now, Logoist and Texture Package, I should say they are paid apps, but they're actually relatively reasonable. It's like maybe 60 euros for the two together, and you get a lot of features, but I know that it's not free, so sorry about that too. So finally, I needed a background for the kitchen, and I'll show this quickly. So I asked AI for a large, wide kitchen, and I got this instead, and I gave up. So instead, I just looked for some online images, and I broke them apart to give them that illustrated style. And in the end, I went with this one because of its depth, proportions, and limited color palette. After all, it's a static background. Okay, until now, we've not paid any attention to fonts. And with everything defaulting to Arial, the game didn't look like a game, right? There's thousands of fonts. I didn't know which one to choose, but I wanted something playful and somewhat modern and not too overly cartoonish. So I settled on Arco, and I added the CSS to the CSS file. I was really surprised to see how adding a single custom font kind of makes the game pop and look like a real game. It's much more intentional, but it does have a problem. When the game first loaded, the text was misaligned, and I thought it was maybe related to Canva text component. But then I realized, of course, it was a font loading issue. Now, on websites, there's lots of terms for this, and they all basically mean your font's still missing. But in a game where loading assets is kind of expected, we have state machines, and they can help here. So I already had a loading state for my state machine, and now I was able to load fonts and sprites. And I used a library called Font Face Observer, which monitors the loading of fonts and returns a promise when you call it. Everything now looks aligned from the start. Okay, and with this font, I was able to put the pieces together and make a new, whatever, title. So the new title for my game is Egg Drop, What's Up? Okay, we can drop the screen in the title for the game now. And Chef Raffi, you see, has grown bigger. He can also pivot and face the direction he's moving. We have a new scoreboard and also a scoreboard between levels. But I'm going to move on a little bit here. Okay, so the game looks good, but what about sounds? Well, the majority of the game's sound effects were recorded by me and my own team. That's me, Raffi, and his sister Mila. And once we've recorded the sounds, I brought in the audio clips to Audacity. That is free, it's open source, and it's an editor where you can select and trim sounds. I used Howler.js to add the sounds to the game. And that makes it really easy to import them and control the audio files. Here you see there's a music clip that loops, and there's other individual sound effects, each with their own volume setting. You can even create audio sprites. But in the state machine, XState has something known as actions, which are basically for fire and forget side effects. But in this case, that's sound effects. So for example, whenever an egg lands on the floor, we can use the action to play the right sound. We'll hear those a little later. Okay, now that I have my game development well underway, I wanted to talk about the genetic algorithm adding that. So I had roughly 2 goals in adding a GA to the game. One was to make the game more challenging with each level, and the other is to kind of just observe how the game reacts or adjusts in real time to the particular player. So in GA terminology, I knew my hens would be the individuals, so I now call them hendividuals. Since their eggs hatched and turned into chicks, it actually seemed fitting that their own chicks would basically indirectly represent the next generation. Now, the first approach was to take some characteristics for each hen that I wanted to vary across the population, like speed and tween duration, movement distance, maximum eggs, things like that. And I inserted all the execution stages of the GA, like fitness evaluation, selection, crossover, and mutation, in between the levels of gameplay to produce a new generation of hens. Okay, I created a fitness function to evaluate performance after each level. I rewarded hens who laid more eggs. I rewarded hens if those eggs didn't get caught, or added a bonus if their black eggs got caught. I punished hens that didn't lay any eggs at all. Okay, so the game was now working with a running GA, but I just wasn't sure if the GA was working as expected. I mean, I couldn't tell if the game was getting harder or easier. Was it a matter of time playing it? Was there something about the game that just doesn't work with the GA? So I was faced with the dilemma. On one hand, I needed to know how to tweak the GA in order to make this game more playable. But I also needed to finish building the game in order to play it and to test the effectiveness of the GA. Which do I do first? So I decided to take a break from development and to think it through. Now, a GA needs variation and a sizable population so that it can put forth enough potential candidate solutions. I've only got about 10 hens pacing back and forth on that beam up there. So I realized that population size was just too small to work with. So believe me, I tried to simply crank up the population size, but this led to crowding and chaos. Performed pretty well. So how could I increase the population without all the hens being visible at the same time? Then I remembered the Kaboom game, where bombs are being dropped. Bombs, I mean, that's it. Each hen can go on a bombing run, right? Instead of sharing the stage simultaneously, they'll go from one side to the other, and they'll have many more hens that way, and they get one chance to drop as many eggs as possible. I can even double the number by making them go both directions. So it seemed like an improvement. The population's larger, but I also tried to think of other ways I might be able to tweak the GA to overcome a limited population size. Maybe adding more genes, tweaking the fitness function, introducing elitism, where you still use a roulette wheel, but then you do reserve some spots for the best performers to guarantee that their genes will be passed on. Maybe other forms of crossover, or changing or increasing the mutation rate. In order to pave the way for experimentation, I created a cleaner separation of code between general GA functions and code for this game. For example, this roulette wheel selection function can easily be swapped out for a different selection method. Another important concept in genetics and GAs is the distinction between the genotype and the phenotype. So for our purposes, a genotype is basically represented as an array of random values from 0 to 1 for each individual. And the phenotype is how do these values translate to behavior characteristics of the hens in the game. So we can create a JavaScript class for the DNA, which holds the genotype array. And each of these values will be assigned at creation. But during crossover, both parents will bring their own existing DNA to produce offspring. And instead of averaging parent values, we can actually go through the DNA one gene at a time and select from one parent to the other. That more closely mimics biology. And we produce a full DNA length for each child, but the genotype is still separate from the actual phenotype values. Okay, so because our values are separate, we can change our mind about what those characteristics are, and we can also set appropriate value ranges for these numbers, and even meta instructions like whether to round numbers. So for each new generation, we calculate the phenotype by multiplying the genotype by the phenotype values within range for each individual. And we can reuse this setup in any application. OK, it all starts to come together for our individual. And on the left, you see we have DNA, phenotype, and fitness. And on the right, we have specific attributes for this hen. Let's take a final look at what the game is like to play. OK, I promise I'll debounce the sounds and lower the volume soon. The game is open source. You can check it out and take a deeper look at the structure, the Canva animations, the state machines, assets, or follow ongoing development. Now, what kind of experience do we get from that? So I'll look at this really quickly, but I collected statistics of each level of the gameplay. I put it in a developer panel. And there's some good signs of the hen attributes actually going in a certain trend. Things like the hen speed, the egg laying rates, the distances they could travel, the average time they would stop. All these things were kind of trending in a particular direction, usually up. But it wasn't all good news. The total eggs laid seemed to be just sort of up and down. The average eggs laid per hen kind of did a bell curve. But as a little bit of a silver lining, the player's catch rate generally did trend downward over time, even if it wasn't as steady as I had hoped. So just one note, this is from one player over 16 generations. There's a lot more work to be done here. So in summary, we've learned about genetic algorithms and why or how they can be useful. We've talked about how to create a web game from scratch using React and Canva and XState. And we've looked at AI and illustration and sprite creation for character assets. And we talked about sounds and playing them in an app. We also looked at the GA and how we can use that to make things a little more dynamic and automated, but with some note to some difficulties that we ran into along the way. In terms of resources, I want to give a shout out to this new book I just got. It's called The Nature of Code by Daniel Schiffman. This book has everything you could ever want about simulating natural behavior and systems in a JavaScript. It's my new favorite book. I really recommend it. So some final thoughts for you here.
Go. What's up? Oh no. Yes. Oh no. Oh no. Ha ha. Ha ha. What's up? Yes. Ha ha. Yes.
Over the course of the past couple of months, I've really fallen in love with game development. I mean, programming is already a very creative field, but building a game takes that to a whole nother level. Working with the GA in a game, to me, admittedly feels a little experimental. But once the mechanism is in place, it's really fun to see the game almost come to life and take on a life of its own. If any of you have ever wanted to start to build a game, I really encourage you to do it. It's a lot of fun. And if you have cool projects of your own, or you want to talk about building a game, or you just want to go to the Video Game Museum in Malaga, I hope you'll come up and talk to me sometime during the conference. Fala Manogu, thank you so much. You've been a great audience. Thank you.